Thank you all so much for having me. I'm really excited to be here and really excited to tell you about this project. So please just, this will be much more fun for me and much more useful if you interrupt when you're confused or if you have questions. And if we don't get through all the content, that's OK. OK. All right, so this project it's titled Theoretical Guarantees in the Search for Less Discriminatory Algorithms. And I think my goals are to describe for you all what less discriminatory algorithms mean, what the sort of concept is, introduce a, I think, fun sequential decision-making problem related to this search for less discriminatory algorithms, and then one solution which we came up with, but we think there are lots of sort of neighboring and related problems and possibly other techniques that you could use here. So I hope to sort of get you excited about some of the theory aspects of this as well. And this is work with friends and colleagues, Ben, Solon, and Manish. OK, so what is a less discriminatory algorithm? We'll start with just sort of the basic foundations that ML models are being used in these sort of high-stakes decision-making settings like housing, employment, and credit, and they can perpetuate or exacerbate social biases. So the idea is that firms should be searching for less discriminatory algorithms, and this is specifically a proposal that's come out of the legal literature. Okay, so this might be impossible for you to see, but I'm just going to give you sort of a primer on where this comes from in the legal framing. And here's the sort of simple chart to help you understand the discrimination law. So you come in with an employment practice or policy. You ask a first question, which is, does it cause a disparate impact on a protected group? Well, we could define disparate impact different ways, but usually we mean selection rate across demographic groups. So there's like a baseline selection rate. So I give you a loan with a certain probability if you're marginally over the whole group. And take that average for like a reference group or the whole group and subtract off that average for the protected group, and that's what we call disparate impact. So if there's no disparate impact, it's a lawful practice. And if there is, you have to ask more questions. The next question you ask is the practice related and consistent with business necessity? If you've ever sort of been in a room with the sort of discrimination law people, this is the one that you usually hear. It's like business necessity. So the example will be something like, if there's a job that requires lifting heavy objects, it's OK to impose a strength test and have, say, different gender groups have different pass rates, as long as the test is sort of consistent with the business necessity. So having a strength test for a computer job would not be appropriate and would be unlawful. A strength test for some job that requires lifting heavy objects would be allowed. So if it's consistent with business necessity, there's one final check, which is there a less discriminatory alternative? And if there is one, the company is legally required to adopt it, or else it's breaking the law. OK, so less discriminatory algorithms just replaces alternative with algorithms. That's sort of all you need to know. And the goal is to find an equally performant model. That's what we mean by like business necessity. So you don't need to give up anything according to the law, but one that is less discriminatory. And so you might ask, is this even a reasonable thing? Does this ever exist, these less discriminatory algorithms? And one of the things that has come out of it's called a model multiplicity literature, shows that models that are optimized for accuracy can vary a lot with respect to other performance measures. So for example, this like difference in selection rate across demographic groups. And this is true even if the training procedure used is exactly the same. OK, so then you might ask, like, how do we know how much to search? And there's a quote from this financial services blog. The financial services people think that they are legally required to search for alternatives, but they don't really know how to approach it, right? So they ask, no constraints or limits on the search have been proposed, and it's unclear how much resources, time, and effort are expected in searching for these potential LDAs. And so it's sort of a question like, yeah, legally, what is required? How should you even go about answering this question? And so this is the question that we're thinking about today. Okay. All right, so there are a few challenges with this. First is that we don't know all that much about the results of a model training process. Like they're kind of these weird artifacts that come from like a lot of like engineering, a lot of like, it's rarely a convex optimization problem that we're knowing where we like know the result or can sort of characterize the distribution of outputs. So first of all, the disparate impact of, or the distribution of model disparate impacts after retraining models is totally unknown. It's also true that we don't even observe the true disparate impact for a given model because, of course, we're always evaluating on a finite data set. So even if you get some IID sample from the population of interest, you might not expect to, you might have some estimation error. OK, so I'm going to start building up to thinking about how we characterize this problem sort of in a statistical sense. But the first sort of model ingredient that we want is these two factors I listed before, uncertainty about the disparate impact distribution and sampling error. We also have some intuition that like it's unreasonable to ask a firm to continue training models forever in the hopes that they will eventually find a model with lower disparate impact. And one way to describe that is there's some like incremental or like marginal costs associated with training a model, and we should expect that we should stop training once the benefits from training more models fall below this marginal cost. And our goal is a little different than other problems you might encounter in TCS, which is that we're going to hope for like evidence or certification that expected benefits of training more models is small. It's not that we want to like maximize expected utility, I'll get into this, but we want to provide sort of statistical evidence that we have searched enough. And so it ends up having this sort of principal agent flavor where you'd like to be able to come to either a court or your compliance team or your manager and explain to them what you've done and why it's a reasonable thing. OK, and so the way this is going to work is it's a sequential decision-making problem where we have time indexed by t. And at each time iteration, you pay a cost to train another model. The next thing that you do is sample a new model and observe some noisy estimate of the performance, where even the distribution of these noisy estimates is unknown. There's also some true underlying population disparate impact or performance, and that's both unobserved and unknown. And so your only question is, should I keep going or should I stop? Yeah?
Sorry, what was the tilde representing?
Oh, just sampling from a distribution, and these are all IID. Good. And so at the end of this process, when you decide to stop, we'll take the performance of the model with the best, or we'll take the model with the best observed performance. So we'll just take an argument over these Q hats, and that's the sort of index of the model that we're taking. And since we're going to work with minimums a lot, I'm going to define a new symbol, U hat t and UT, to describe that minimum. So it's the performance of the model with the best observed performance and the true performance of the model with the best observed performance. And like disparate impact, where it's sort of a difference between two numbers between 0 and 1, if you took their absolute value, for example, or you know that the reference group never has a selection rate lower than the protected group, we know that these quantities are bounded, and so this is the assumption that we're going to make. Yeah?
Could you explain your subscripts S and T?
Right. So to find the index of the best performing model, we're going to search over the best performing model up to time t. We're going to search over all models up to time t for the model. So search over s less than or equal to t for all models, or for the model up to time t with the lowest observed disparate impact.
Okay, thank you.
Good. And formally, our goal is to choose a stopping time tau such that with high probability, the expected benefits of training another model, so take the minimum at time tau minus the minimum at time tau plus 1, conditional on what we've seen so far, and certify that it's less than the cost of training another model. And so this expectation, because we're conditioning on tau, is just over sort of the unobserved random variables and over time tau plus 1. And so the way to interpret this is the marginal benefits of training another model are not worth the costs.
Can I ask how you express both sides of this equation in the same terms?
Yeah. This is not an obvious thing, right? Like training models, even computing the marginal cost of training a model is not obvious. Like, are we talking about seconds or dollars or engineering time? And then we need to somehow also translate that back into disparate impact units. So first of all, I have very little to say about this. I don't know, and like this, I think, is something that's going to depend a lot on the context. The only slight grace that we get is that the choice of gamma doesn't matter very much. So if you choose gamma, stop, and then decide it wasn't good enough, you can keep going, and you don't have to throw away your previous work. So you can debate about it, right? Like if you choose gamma that's too low, you'll do extra work than you would have had to choose. But if you choose too high, you can stop, have a conversation with your compliance, and then keep going. But how to translate seconds into disparate impact units, it's not obvious. I think this is just a heuristic that if you're training ChatGPT, you probably have the budget to train about one model. And if you're training a random forest, then I can train 10,000 in a second. And I'm pretty indifferent between waiting for a second for my models to train and 10,000th of a second.
But I guess I'm a little bit confused about why this isn't hopeless in the case in which there's a single low probability model that performs very well with respect to whatever U is. Somehow the normalization between 0 and 1 is supposed to be saving you, or?
Well, if there's a single model and the space of models is very large, then you'll see that model with low probability, and so then that's included in this.
Oh, I see. Okay. I should have read what you wrote.
Right, so we're not going to get the least discriminatory algorithm in general. And maybe there is this sort of pot of gold at the end of the rainbow.
What does high probability mean for you?
Oh, just wrap this whole expression with probability that this whole expression holds is greater than or equal to 1 minus delta for a delta that you fixed in advance.
That you fixed it.
In advance.
Okay.
Will delta be a function of any of these?
No, delta is an input but certainly tau will depend on delta. So depending on how confident you want to be, if you're more confident, you'll need to search. You want higher confidence, you need to search longer. Okay. All right, so there are many related formulations, and the sort of computer science and economics literatures have both asked similar questions for a very, very long time. So you might have seen a Pandora's box problem, where reward distributions are known rather than unknown. Also, secretary problems, where you keep the last seen rather than the best seen so far. So you get this sort of you're hiring a secretary and you need to either reject the job applicant or hire the one that you have in front of you. This is also true, right? We were talking earlier about profit inequalities and other optimal stopping. You're often optimizing for a different objective, right? Either maximizing utility or some cumulative reward over the course of in a bandits setting, cumulative reward rather than providing this sort of certification, which is arguably important in our setting. So I think this problem is new and pretty natural and a close neighbor of many of these problems, but different, and we'll use pretty different techniques. It's also not really true that we need much from the search for less discriminatory algorithms to motivate this problem. So there are several other sort of situations that this could describe, right? You might want to certify to a reviewer that you've searched sufficiently hard for a strong benchmark model. You've retrained some models and seen that no, actually I didn't cherry pick the benchmark that I'm comparing myself to. You could also describe sort of random hyperparameter search where you want to certify to your advisor or your manager that you've searched sufficiently hard over the hyperparameters. Or other sort of principal agent sequential search problems. And yeah, I'm very curious, if you have ideas about other sorts of problems that this might describe, I want to know them. Okay, all right, so with all of that set up, let's start to dive into the theory here. Remember, the goal is to certify with high probability, or provide this high probability guarantee that the marginal benefits of training another model are less than the cost of training another model.
Okay, sorry, I'm still actually confused by my original question.
Yeah.
If sort of the amount of the improvement of the model is unbounded, you can imagine that there's a single low probability event that just totally dictates what the expectation is because the scale.
Well, okay, here's where bounding is helpful.
Yeah. But is that I feel like you can just simulate this case. I mean, this shouldn't be the case where you're going to tell us why you can do this. I'm just trying to understand the model. So this, you can basically simulate this case where basically all of the whatever the U's are, I forget what you're calling U's, but whatever the U's are all
performance.
1 over poly n, or I don't even know what it is, but some really small, vanishingly small thing, and then there's this one thing that's very close to 1, where I'm assuming 1 is the good side.
Yeah, sorry, I should have said 0 is the good thing, but yes, I'm following you.
And it's basically 0, oh.
Yeah.
Well, if this expectation is very small, he just stops, right?
If the expectations is very small, it stops.
Right, but you can't tell that the expectation is small. Well, okay, I think I have benefit versus cost flipped in my head or something. The expectation.
Or you just keep searching forever until you find this gem and find it in the run.
But I think this only works if it's a model of cost, not benefit, right? If you're trying to, if it was more like a secondary problem and you were trying to get a good solution, but it was very low probability, very high value, you wouldn't be able to tell that your expectation is positive unless you actually found that gem. Whereas in this case,
As long as we're sampling IID, we can start to bound the probability that we see something very different from what we've seen so far, for example. And in which case, if we've seen a lot of stuff already, then the stuff, the pot of gold, can't be very large. The chance that you see something new can't be very large. And then the benefit itself, conditional on seeing, we'll get into this, but the benefit is bounded because the whole thing is we have a u tau minus u tau plus 1. Both of these numbers are between 0 and 1, and u tau is less than or equal to u. So the whole expression can be between 0 and 1. So the probability of seeing a new model that's better at all is small. This expectation is small.
but I guess then the sort of sample complexity of this, the point at which you start being able to reason about probability, your uniform over n different models, you better see on the order of n if you pick one. There's something, I don't know, if you're allowed to prepare adversarial distributions over these things, it seems like something about
The bounds might be kind of weak, yeah.
Yeah, the bounds will be dictated by something about the distribution.
We can check. I mean, we ran this on some data sets, and we can look at them together and see if it seems.
I'm sure this doesn't happen in practice, but.
Or the bounds might be, but if the bounds have to hold even for adversarial distributions, right? So the bounds could be.
Okay.
Uh,
Say not that much.
But your question is not on what is the guarantee. Your question is on how to achieve this guarantee, right? Which hasn't told us.
I guess given the stated model, I just wanted to understand why
Yeah.
it's impossible.
Yeah.
Interesting.
Yeah, these are good questions.
is the training procedure the same for each of these models? So like each step, it's the same training procedure,
Yeah.
and you're just like taking a new model from the like predictive multiplicity like equivalence class.
Yeah.
Models.
That's right. So I think I'll get to this eventually, but like that's obviously, you might want to do something smarter than that, right?
Yeah.
Than just like retraining.
Yeah.
It's also a question.
Oh yeah.
Is the value of u tau supposed to be smaller the better it is?
Mhm.
Okay.
So small is good. Everything's between 0 and 1, and u tau is at least as large as u tau plus 1 because u tau is taking a minimum over the first tau, and u tau plus 1 is taking a minimum over the first tau plus 1. Good. All right, so our plan is to work through some different levels of sort of increasing problem complexity, starting with like as much information as you could possibly hope to know, like model performance distribution and performance being observed exactly. A version of this where the model performance is unknown still, is unknown, but the performance is observed exactly still. And then finally, the realistic case where both the model performance distribution and the performance itself are sort of unknown. And if we don't get to the third, I think that's fine. That like sort of interesting stuff happens in tier 2. So I'll argue that 1 is like totally trivial, 2 is interesting, and 3 is like a minor modification of 2. Okay, so full information means that the distribution that we're drawing from is known, and we get to exactly observe QTs rather than Q hats. So let's look at a little example. Here I've drawn this random mixture of Gaussians. And on the x-axis, we have performance. On the y-axis, we have the density. But we know the distribution, so we can exactly compute this expectation for any one of these u taus. And we can also figure out the smallest like little u, such that it's still worth sampling if ut is equal to u, and stop whenever we get below that point. So in other words, the only thing that we need to know is, the latest sample that we've seen so far, is it below or above a threshold? And so, let's say I've computed this integral. I've figured out the point on the x-axis where if I see any samples to the left, again, left is good, I stop. And until that point, I keep sampling. Okay, so I drew some random variables from this distribution. In this particular instance, I drew a bunch of them until I reached the stopping condition, 7 of them, I guess. And this is a mixture of like 1/10 and 9/10, so maybe 7 is a good number. The only thing, we'll look at these diagrams again before, but just again, notation, the U is the minimum seen so far. Q's are just the samples that we've seen so far. And so I'm drawing the minimum in black and the samples seen so far as gray. OK, so that's it. Sample until you reach a threshold, and then you stop. OK, so now we'll get to the interesting case where we don't know the distribution we're sampling from, but we do observe the draws from that distribution exactly. Okay, so now I'm drawing a plot, and I've just put a bunch more confusing mixtures of Gaussian. Like they don't even, they obviously don't need to be Gaussian distributions. They can be anything, but I'm just going to sort of say that we're like in this haze of possible distributions, and we have no idea what we should do. So if we draw the same sequence of plots, we eventually hit this U7, and we might reasonably ask at any of these points, should we stop? I mean, we've drawn 5 models in a row that are all close to each other. Maybe that's evidence that there's not that much. Anyway, now we've drawn a better one. Maybe there's an even better one if we just sample a few more times.
Sorry to.
No, please.
What is density in this instance?
The probability density over the random variable QT.
Okay, thank you.
Okay, so now I think we're getting closer to the heart of the question, which is we have this expectation, like, just how should we hope to try and say anything about it? And the first observation, right, is that since ut plus 1 is less than or equal to ut, we can just use law of total probability to say if they're equal to each other, then that expectation term is 0. And so the only thing that we need to characterize is the expectation given that ut plus 1 is strictly less than ut times the probability of that happening. And so why is this reasonable? Well, hopefully we can bound this probability so that it's going to 0. And then this term over here is at most 1. So if the right term goes to 0, left term, the product of the terms goes to 0. Okay, so I just replaced each of these longer expressions with shorthands because we're going to bound each of these separately. But the expectation conditional on improvement is mu, and the probability of improvement is p. I'll call the left one the conditional expected improvement, and the right one improvement probability. Okay, all right, so now one at a time we're going to bound each of these. The mu one, we're not going to do anything particularly interesting. So just remember I've put the definition of mu on the board. I think oh, good. So, all right, so our goal is an almost sure uniform upper bound on mu bar. Of course, you could do like a high probability bound, but like for now, let's just work with this. And trivially, mu ut is less than equal to ut, simply because ut plus 1 is less than or equal to ut, and the minimum that you could achieve is 0. So in these adversarial cases, you can't do much better than this because you could have seen ut, and there'd be no probability mass between ut and 0, and there's a point mass at 0. Of course, you might think that this is not, in general, going to occur in the world, and so you can impose more assumptions if you know something about the data generating process. So for example, if you assume that the distribution has a subuniform left tail, then you can sort of split this in two. If you assume sharper tails, then you can do better bounds. And if you know that the disparate impact is bounded away from 0 by some amount, you can, of course, shrink down all of your intervals. Okay, so this is just to say that if you have distributional information, then you can use that distributional information to get sharper bounds. So that's all we're going to do for mu. Okay, so the fun part is p. P is the probability that we see a new model that was strictly better than the one that we've seen already. And we want such a p that with high probability, so with probability at least 1 minus delta, this upper bound p bar, and it's going to be time indexed, it's going to evolve over time, is at the stopping time greater than or equal to the true probability. Okay, so it might seem like this is, let's just sort of sit with this for a second. But like in classical statistics, we're usually used to thinking about fixing a sample size in advance and then making high probability statements about them. So we're usually saying something like, fix n. After you fix n, the probability that you reject the null hypothesis is, falsely reject the null hypothesis is no less than 1 minus delta for whatever your desired type 2 error rate is. So that kind of thing. And we could do this if we were to say, like, we'd like to run a fixed number of model training processes and then characterize this probability. We could, of course, do that, but that's not what we're doing here. We'd like to know when to stop adaptively from the data. In other words, we want this bound to hold for all t, and so we're going to switch the order of quantifiers. and say that the probability that this holds for all t is at least 1 minus delta. And these are called anytime valid bounds. And our techniques, we're going to draw a lot from this like very nice literature on anytime valid inference. Okay, so you should see that like the top guarantee is a lot weaker than the bottom guarantee, so you're going to trade off some width in confidence intervals in exchange for this adaptability. Okay, all right. So here we are at the sort of main technical like nugget from this paper, and I'm going to phrase it in sort of generic random variable terms because I think that it might be useful in other contexts. So let's say we have a sequence of random variables drawn from a distribution P. And we have defined, like before, a minimum yt, which is the minimum over the x's up to that time. For any failure probability alpha, so that's like our sort of type 2 error in the stat sense, we're going to define for any t greater than 2 this expression. And it might be a good idea to verify for yourself that this expression goes to 0. So if t goes really large, that exponent dominates, and you get something to the 0. It's 1. 1 minus 1 is 0. And the guarantee that we're going to prove is that this anytime valid high probability guarantee says the probability over the next sample being less than the one that we've seen so far, being greater than our high probability bound is not too large. So this is like sort of the inverse of what we said before, right? Where we say like our upper bound holds over all t with high probability. And so I just want to interpret this for you. And we can think about actually drawing sequences of random variables and plotting this bound. So in gray, I plotted a sequence of trajectories of uniform random variables where I just plot the running minimum. So you can see it sort of steps down every time you see a new minimum. And I've plotted like 100 of them. X-axis is time, y-axis is this running minimum on a log scale. Then our upper bound is this blue dashed line. And the guarantee that we can expect is that on average across all of these 100 lines, fewer than 5 of them should cross the blue line at any point. So you can see there's one that sort of pokes out over the blue line. That's one of the events where our bound fails. And then maybe up here too, it's kind of hard to tell. Okay, and so I'm going to try and prove it. I'll argue that we could just consider the case that the x's are uniform on a unit interval. And the reason is that we can always transform a random variable into its quantile as long as we define it appropriately. So point masses, we can figure out a way to sort of work around the fact that not all quantiles exist, such that it's always true that the probability of seeing a new sample less than the best sample so far is equal to that yt. If it's easier to think about, continuous random variables are perfectly fine to think about. So you draw a bunch of uniform random variables. The probability that you see, the best one I've seen so far is 0.2. We know the probability of drawing a random variable better than 0.2 is 0.2 itself. And the technique that I think is very fun is the strategy of upper bounding by analyzing a fair betting game. And Aditya Ramdas has like really excellent work which explains this approach and from where I learned all of this. Okay, so I'm going to try and describe what this fair betting game is. We'll just first introduce a little more notation. Say money at time t is mt. We're not going to allow debt. So once you lose all your money, you can't like sort of borrow more or something like that. And each bet is mean 0. That is, at time t plus 1, the conditional on everything that you've done so far, the expectation of that random variable is just the previous time step. So you might recognize this as a martingale, specifically a non-negative martingale. But it's also fine to think about this as like a betting game where I say, like, at the next time step, I'll double your money or take all of it. And that's fair, right? Because with probability half, your money doubles. With probability half, it goes to 0. Average those out, and your expected money from the current time step is the same. And a simple argument shows that no one can make money in this game on average. This is Ville's inequality. It says if the two conditions, so the non-negativity and the martingale property, are satisfied, then for any alpha, this threshold, the probability that you see a time step such that your money at time t is greater than a 1 over alpha multiple of the starting money is less than or equal to alpha. And you might sort of recognize this as like a sort of analog to Markov's inequalities for martingales. Ville's inequality is like also fun to think about, I think. So I'm going to give you the proof of that. So we're going to let tau be the first time that MT is greater than that threshold. This is the bad event that we're going to bound the probability of, and let it be infinity if it never happens. Note that because of this sort of fairness of the betting game, the expected money on any one time step is exactly what you started with. And since we stopped at time tau, m sub tau is at least m naught over alpha. This is literally just what the stopping condition says. Then just plugging these things all together, we see that m naught is equal to the expectation of m tau. Use the law of total probability for any t, split that up into two terms. The second term, this term over here, is a bunch of non-negative, the expectation of a non-negative random variable. Probability is also non-negative. So this whole term is non-negative. So we can discard it to get a lower bound. Since we stopped at time tau less than or equal to t, we know that we have the money that we said we were going to stop after. And we can just rearrange this left term with this bottom term to get the probability that after capital T time steps, you've stopped is less than or equal to alpha. Now this is for finite t, but if you take a limit, then you get this infinite. OK. All right, so that was Ville's inequality. It tells us that if we can define a non-negative martingale such that this property holds, if we define a non-negative martingale, this property holds, and if we relate that non-negative martingale to the condition, the bad event that we don't want to happen, this p of yt being greater than our upper bound, then we can apply this inequality and show that this upper bound is an anytime valid bound on the true probability, conditional probability. OK, so here's our simple sequence of bets. We're going to parameterize it by some new random or some new parameter theta, and we'll say that at time t, if the minimum that we've seen so far is greater than theta, I'll give you a 1 over 1 minus theta factor improvement of your money. So if theta were half, then I'd say every time you see a yt greater than a half, I'll double your money. And once you see a yt less than 1/2, I'm taking all of it. It's a fair betting game. It's non-negative. And it's true for any theta. And if you just think about the theta equals a half case, you can convince yourself this is a fair betting game. But of course, it's still true for any theta. So now I'm going to relate yt to our martingale mt. The left is yt. The right is martingale mt. Both x-axes are time steps. The y-axes are the respective quantities. So left, running minimum. Right are sort of current money. So I've just drawn a single sequence of random variables, which in this case starts at roughly 1, and then drops down to half, then maybe 0.4, then 0.35 or something like that. And I've plotted a bunch of thetas for which basically in this regime, the sort of gambler loses all their money sort of within a few time steps. So you can see that if you draw a few more trajectories, you can trace out these plots, and you see that whenever the trajectory stays high for a while, so this sort of top trajectory up over here, money increases exponentially. Both of these are on a log scale. So money increases exponentially until yt drops below a threshold, and then money is 0 for the rest of time. Depending on what theta is, determines the sort of parameter on that exponential growth. So do this 10 more times. You see that the trajectory of money stays the same. Like for whatever theta, I multiply it by 2 or whatever every time, and then at a certain point, it goes to 0. So now I'm going to relate Wield's inequality on the right to something that we care about, which is the minimum over a bunch of uniform random variables, which is on the left. Wield's inequality tells us that over all time steps for any one of these thetas, the money cannot cross that 1 over alpha threshold. So bad event was this green line, where at theta 0.3, there was some period where the money was greater than 1 over alpha. But good events were these orange and green lines, also like many of the trajectories where the money stays over all time below this threshold. Now translating this over to the right, actually, hold on. The other thing to note is that if your money is going to grow, if the martingale is going to grow above 1 over alpha, it's always going to hit 1 over alpha at the same point, because you follow the same slope up until money goes to 0. So you can just figure out what that time step is for any given theta. So I'm going to draw that a line for each of theta equals 0.1, 0.2, 0.3 on the left, starting at that point when it would hit. Because before that point, no matter what happens to this martingale, it's going to be less than 1 over alpha. So you should only start to worry after the point at which it's conceivable that you could have crossed the boundary. And so the bound on the right translated to the one on the left just says that if at any point one of these gray thresholds crosses over one of these lines, we have a bad event. Otherwise, we have good events. So this point over here is the same as this point over here, where we say a bad event happened, a violation of our high probability guarantee. But the last sort of magic reveal is that martingales obey this sort of fun thing where you can take mixtures of them. So you can say with probability half, I'm going to take martingale 1, and probability half, I'm going to take martingale 2, or even a uniform mixture over the whole line, alpha 0 to alpha 1. If you do that, you still have a non-negative martingale. And the plot that you get is this dashed red line on the left. And then it's much more complicated. It's not that easy to see what the trajectories are doing the same way that it was in the sort of simple single theta case. But you get this you get to smooth out over these different values of theta. OK, all right. So that's sort of the technical meat. We're just going to come back together, pull everything together and say, we've upper bounded. We've done this sort of dumb upper bound for mu. We have a sort of fun upper bound for p. And if we just multiply those together, the first one is a almost sure guarantee. The other one is a 1 minus delta guarantee. Multiply those two things together. So we have u tau times p bar tau as a time uniform upper bound on the quantity that we wanted. And this is going to be our stopping condition. Whenever our upper bound drops below theta, we can conclude with high confidence that the marginal benefits of retraining are no longer worth the costs. And this is the guarantee that we'll provide. At the time that you stop, the marginal benefit from retraining is probably not greater than the cost with high probability. Good. So okay, so I mentioned there's a mixing over different distributions. You get to choose what kind of mixture you want. So you can choose different mixtures. And in fact, so blue is the one that I just showed you. Green looks indistinguishable, but is sort of is the sort of optimal mixture that we can prove in this setting. And so for the sort of theorists in the audience, this sort of first bound is a log t over t. The second one is a log t over t. Like I think to any reasonable person, like you might not care about this, but the second one is in fact asymptotically optimal. And so, yeah, we can. There are these classical results that say that the running min of uniforms crosses this log t over t boundary infinitely often. And so if you've seen this before, like law of iterated logarithms says exactly this, but for means or for sums rather than for minima. Okay, all right, in the last few minutes, we're going to just breeze through the finite data. This time we have these two distributions. One is the sort of observed disparate impact, and then we no longer get to observe the true disparate impact or the true performance. So Q hat is observed, Q is the true unobserved disparate impact. So we're back in this situation, but now we have an additional line where we have a U hat, which is observed, a U, which is unobserved, and we get these sort of pairs of random variables where all we have to go on is the blue lines rather than the black line. Okay, so this time we're going to put a hat on the conditioning. Before, our guarantees were with respect to the truth. Now we're going to say with respect to the observed performance. And the only thing that we're going to do is add and subtract terms. The second term looks a lot like the term without hats, and we can just pretend as if they were the truth. The the first term just says that the difference between how wrong you are at time tau and at time tau plus 1 must be non-increasing. And then we can ignore it. And this is sort of like saying like regression to the mean only increases. Okay. The last little thing that I wanted to show was experiments on a bunch of data sets and a bunch of simple model classes where we show sort of the truth by synthetically creating a population and then subsampling from it, and then our procedure. I think the thing that I take away from this is that retraining models doesn't get you that much in the first place. So the green line drops below like 0.0 or 0.1%, like pretty quickly for most of these models. So if you're hoping to get like a 0.1% improvement in disparate impact, at least in these sort of synthetic settings, you shouldn't expect to train more than like 60 models. And often you shouldn't train like 10 models. And that's kind of it. So we just talked about this new non-parametric sequential sampling problem motivated by the search for less discriminatory algorithms with a solution using anytime valid inference and this idea of like inference via betting. We already got questions about this, but the choice of gamma is not obvious. Like this is not an easy question to answer, and we have like very little to contribute here. But the saving grace is that you can sort of have a debate about what gamma should be, and because you just continue sampling and these guarantees are anytime valid, there's nothing saying you have to stop once. You can stop and then restart, and that's fine. The other question that we got was, do we have to keep the training process the same? It'd be nice to think about distribution adaptive searches, but I'm not really sure how to think about this in like a sensible manner, right? Because if you always change the distribution a lot, you're not getting a lot of repeat information across time. Okay. So thanks so much. This is gonna not online yet, but I'm happy to talk more details, and it should be online in like the next week, hopefully. Yeah, please email and reach out, and thanks.